Thank you everyone for coming to the seminar. So today Vishnu and PU both will present their latest work on the safe controls that's built on control barrier functions. Vishnu is wrapping up his PhD. Hopefully in summer he will defend his PhD while PU is gaining momentum on her research side. This work is the exploration sort of a work. Part of the Carmen project. Carmen project is safe navigation under PNT, position, navigation, and timing concerns. But also on the control side, which Vishnu is looking into, is mostly his PhD work on using control barrier functions for waypoint navigation. So Vishnu,
Thank you, Professor, for the nice introduction. So, in today's research seminar series, we'll be talking about the development of autonomous vehicle controller with safety guarantees using control barrier function. So, to start with the motivation of this work, so safety is the highest priority for autonomous driving. So, we have come across a lot of scenarios in the news and highlights on how AVs go through the safety violation. So some of these incidents are like Waymo killing a dog, which is actually much better than Uber killing a pedestrian, or a driver hitting a pedestrian by some company in the Bay Area. So now, so here we see people blocking autonomous cars by using traffic cones. So by which they can block or stop the autonomous roads from the vehicle. So by seeing these incidents and safety incidents on autonomous vehicles, uh, are the safety violation of AVs causing public to lose hope on the AV adaptation? So can we assure, like as we see in these incidents, are AVs actually that unsafe? Is there a way where we can quantify or impose strict safety on the AV operation? So So even though we have traffic and environment in which the autonomous vehicle operate being highly dynamic and highly unpredictable, could we still guarantee safety? So here we come up with a video where we develop a controller and test with an extreme scenario where the controller is put through a pedestrian who jumps in front of the vehicle within the 10-meter radius of the vehicle. So here we want to see if the controller is able to avoid the pedestrian, and that's what we'll be seeing how we develop this controller through this seminar presentation. So So yes, it's indeed a dumb thing to jump in front of 10 meters in front of an autonomous vehicle. So is the controller actually well designed so that it can handle such situation is what we are going to see through in this presentation. So most ADAS systems help in crash reduction. As this study perfectly shows us, does ADAS system actually help in crash reduction? Yes. Yes and no. So yes, it reduces crash reduction in cases of lane keep assist, where it reduced 19% crash reduction, driver monitoring system, which contributed for 14%, and emergency braking, which contributed for 10%. But also no, it increased the crash rates while operating in cruise control and adaptive cruise control. So does it actually mean which should actually be an open-ended discussion. So does it mean our public overly relying on these technologies without a comprehensive understanding of how these systems actually work? And are the general public very well informed on how these systems work and what are the safety fields in which these ADAS systems are designed to operate in? Are they very well aware of the ODD? So this remains an open-ended question. But in this presentation today, we will see how we started a journey from the auto drive vehicle, which is a very well equipped vehicle with 3 LiDARs for the front perception. We have 3 cameras and 1 long range camera. We have GNS sensor with multiple GNS antenna and And we have a real-time kinematics, which gives us very precise centimeter level accuracy GPS signal. It's embedded with V2X, which enhances the vehicle's localization and like the environment perception ability. So we have a really powerful onboard computer, which is an Intel machine, which we use for the entire autonomy stack. So this presentation is where we took an autonomous vehicle and we guarantee and we put it in front of a dynamic obstacle avoidance scenario with safety control for fast execution and nonlinear systems. So here the vehicle is completely autonomous and it avoids the static obstacle. And in the first case, you saw it was a dynamic obstacle on the environment and how it navigates safely with fast execution on nonlinear systems. So to start with, what is a safe control? So the safe control in theory is defined through the controlled invariant sets. So let us consider a set Xs, which is a set of all admissible states. So Xi is a controlled invariant set or a safe set if and only if Xi is a subset of Xs and there exists a control U such that for all X belonging to Xi, it could render the next state of the entire system upon implementing the control to be safe. So here you call it a controlled invariant set. So you implement and control U, so which keeps the system within the safe set. So with this definition, where do we actually start? So we have, as I said, a very well-equipped sensor stack. We have a very well-defined perception algorithm, and we have control, which starts from a behavior modeling based on a finite state machine. We have a path planning. We have an MPC controller and safe constraints, which we could implement on the MPC controller. So we start this presentation by starting with the MPC controller. We assume rest of the pipeline is very well established and we get data from the rest of the pipeline in the perfect way. So starting with the MPC controller. So the first question, why an MPC controller and not any PID controllers that we pursued, which have like huge results that has been established and has been used for the past few years. So MPC controller is an optimal controller. So it could handle explicit constraint handling, which means you could define constraints on which the MPC operates. You can define how an input is derived based on the constraints you provide to the MPC. And the final advantage of using an MPC controller is the predictive capability. It predicts the control and states over a time horizon. So we start with the current state measurements which we get from the vehicle, which is the sensor stack, the GPS position, the environment perception, which we get from the vehicle. And then we build the MPC controller based on this data. So the MPC controller itself has like 3 submodules. This is the vehicle model, the constraints we define in which the MPC operates, and the cost function, which is based for the controller to provide the navigation. And then so the MPC controller, based on the reference set point, the MPC controller produces a predicted output and an optimal controller. So the optimal controller and predicted output is for time horizon. And we declare this time horizon like as a design parameter of the MPC. And based on the optimal control input, we implement the first step of the optimal control input to the vehicle. And we repeat the entire process again. We make the state measurement, we pass it through the controller, we predict for the next time step and implement just the first step. So even though we have a prediction, we implement just the first step, making it optimal over the horizon. So starting, like to go back, so we start with the vehicle model, constraints, and cost function. So to start with the vehicle model, we use a vehicle kinematics, a bicycle model, so which is defined by the X and Y position of the vehicle. We have the slip angle, which is given by beta. We have yaw angle, which is given by psi, velocity under which the vehicle travels is given by v. So LF and LR are the center to the front and rear wheel respectively. So we have a discrete time vehicle dynamics model, which is defined by the slip angle beta, X position, Y position, the yaw angle, and the velocity. So thus the states are X, Y, yaw, and velocity, and the inputs are acceleration and steering. So the acceleration A includes the acceleration and braking as inputs. So moving on to the second step of defining constraints in MPC. So we start with the initial state constraint where we initialize the first step of MPC at each time step to the current position. So it's to optimize the calculation. So you don't start all the way from the back. So you start at the current position of the vehicle and you initialize the optimization. So it's quicker to achieve the minimum of the optimization function. So the second one is the state bound constraint, where we specifically impose state bounds on the vehicle velocity. So it helps in safe navigation and collision avoidance. And we obviously don't want to travel 85 miles per hour in a 35 miles. So we try to impose the maximum velocity and minimum velocity, and also we don't want to stop in middle of a highway abruptly. So we impose maximum and minimum velocity constraints so that it remains bounded at our operation. And then we go on with the input bound constraints where we minimize and maximize, like we set a minimum and maximum value of the steering angle and acceleration. So we don't want to have infeasible actuation, like which cannot handle the vehicle, or we don't want to give any steering angle that the vehicle cannot handle. So we bound the acceleration and the steering with the min and max value. So we call this the input bound constraints. And finally, we have the input rate bound constraint, where we set rates on the input, but how much the input, the acceleration or the steering could change over time. So this is mainly to have a smoother input, and we don't want to have like an extreme acceleration or an extreme steering that takes causes very unsmooth rides for the passengers in the vehicle. So moving on finally to the cost function. But before going to the cost function, let's see what reference waypoints are. So how do we set, what's a reference waypoint and how do we get a reference waypoint? So the reference waypoint is just a trajectory where we want the vehicle to go autonomously. So you have a start position and you have an end position, very similar to how you use Google Maps. So you give your start position, like the current position in the vehicle is, and then you give your final destination. So the set of GPS waypoints that are generated that takes you from the current position to the end position, your final destination, is the set of GPS waypoints. So we get this information from the global path planner. So it looks really good when we have it in latitude and longitude. But for the controller, it's more optimal, or it's easier to optimize when you see things in meters, in like SI units. So when you run the perception, it's much easier to have the identification in meters so that you can say like that's an obstacle like 3 meters ahead of you. So to have and coordinate transform in meters, we do a coordinate transform to bring it into Cartesian coordinates. We convert the LA latitude longitude to the east north ENU coordinate system. So now everything looks very neat. East always is our x-axis and north is always our y-axis. And we transform our start and end points from starting from 0, 0 to whatever the endpoint is in the ENU coordinate. So now actually moving to the cost function. So now we have an error-based cost function. So we calculate 5 values of total sub-cost functions where you try to minimize the tracking reference. So now you have a reference x, y, velocity, yaw. So we try to minimize the deviation from the reference. So that's what xt minus xref shows. Qx and qx transpose are weighting functions to bring it to the reference as soon as possible. So we have the x reference, which is, we have the cost function based on x reference, which is from a reference trajectory. We have the cost function from the y ref, we have from the y trajectory. And then optimization goal is to minimize the overall cost function over here. So we calculate the J total, which is sum of all our error-based cost function. And our optimization goal is to minimize the deviation from the reference trajectory. So as I said, we have x ref, y ref, we have velocity reference, like what velocity we need to follow, again, which is again bounded by the velocity constraints. And finally, moving to yaw ref. Do we have a reference yaw? Actually, we do not have a reference yaw. It's practically impossible to collect the reference yaw at each GPS coordinates, like around the entire map the autonomous vehicle is going to try. So how do we calculate the reference yaw? How can we get the reference yaw? So we have the reference trajectory. So to going back to our high school trigonometry, we have the reference trajectory and each point, the reference trajectory is known. So we could calculate the reference yaw by taking tan inverse of y2 minus y1 and x2 minus x1 and use it as a reference yaw. It seems very simple to be implemented and feasible in most cases. I'll tell you why in most cases. So when the car is facing east and we are traveling towards east, so it works perfectly fine because the reference yaw is 0 degree, 0 radians. If it's facing pi by 4, it's again feasible. And if the car is traveling northeast, it's feasible. The yaw reference yaw is pi by 4. It works if you're facing north, perfect. It works if you're facing south, where we consider a pi to minus pi scale as shown above. So it becomes minus pi by 2. It's again feasible if you're facing south. But if you're facing west, exactly west, do you consider it pi or minus pi? And in addition to that, if you have a noise in your measurement, which actually gives you 0.995 or minus 0.995. So is this a problem? And if it's a problem, why is this a problem? So we did this set of experiments. So we initially considered like going from one point to another where it perfectly worked, but it did not work in some parts. So yes, because it causes a discontinuity in the reference tracking. So it works for some cases and did not work well for other cases. So when we ran this MPC controller by calculating the reference yaw based on the waypoint, and we just ran this from the charge station, which is right outside the car, to the gate where we enter the car building. So it ran perfectly well. We have the reference yaw that's perfectly continuous, and the MPC worked. Like we were happy. So we wanted to test this in more directions, starting in more directions and different orientation. And we did the reverse of it. So we started from the gate and wanted to go back to the charging station. So it perfectly worked when we went from the charging station to gate at car. So we start from east and we go north. So we start from east and go north. But now the other case, we start from south and go west. So it causes a discontinuity as soon as we start turning left. So what happens is that the steering goes into an extreme tracking problem and it gets into a wrong direction. In order to get back, it has to go an entire round to get back to the original position, so which causes like extreme steering uncertainty and like takes the vehicle in the wrong direction. And actually, it's pretty ironic. How do you solve it? We have all the heavy companies almost on the west coast, and we cannot go in the west direction. So how did we solve it? So do we always travel in the east, which is not possible? So we switched to a heading error based yaw. So from the GPS and IMU, we have the X and Y position, and we have the yaw angle from the IMU. So this is measured from the vehicle. Then we have the reference waypoint, the closest waypoint that we know from the vehicle. So we calculate psi1, which is the angle between the current position and the closest reference waypoint. So we know this angle by taking tan inverse of y by x. So now we can calculate the required heading angle. We need to get to that point. So this is nothing but the difference between the measured yaw and the calculated angle. So if we implement this, then we know what exactly the car should turn to get to the nearest way. And did it work? Yes, it worked perfectly well in all cases, in all heading angles, all heading directions. But before going this, we will go for a formal mathematical MPC formulation and see how do we mathematically analyze if our MPC is performing well or not. So here we have the cost function, which is represented by J, which is the difference of the squared difference. So we have an convex function. So it is the square difference of the reference with the current state and the input to minimize the input cost as well. So we have the terminal cost, which is shown by P, and the cost function, which we calculated. So we have the vehicle dynamics, we have the input constraints, and we have the input rate constraints and the terminal cost as constraints. So how do we actually guarantee or how do you actually analyze the MPC performance? So we have three factors to analyze the MPC performance, which is feasibility, stability, and optimality. So starting with feasibility. So here XS is the set of all admissible states. So if we have a control input, that's going to keep the entire state within the set of x's, then we have a feasible input. So the u which we input to the system to keep the vehicle within the set of feasible input is a feasible input. And any input that takes the system outside the set of x's is an infeasible input. In simpler words, if real-term MPC solver is not able to identify and control input that satisfies the above condition to keep it within the set x's, then the solution is infeasible. So if you go out of the set, the solution is infeasible, and any input that keeps the system within the set is a feasible solution. So stability. So we analyze the stability using an Lyapunov-based approach. We design a control scheme such that the optimal cost function of our MPC resembles an Lyapunov function. So it satisfies that the difference between the cost function of the current step and the next step is less than 0. So we have a decreasing cost function. So this can practically be achieved by fine-tuning the terminal weight matrix. And in a practical simulation, you could actually see how the cost function is being decreased or how it's being used, which states the stability of our MPC controller. And finally, optimality. So MPC usually results in globally suboptimal solution. So since it's based on a time horizon, it's optimal within the time horizon. And globally, it could be suboptimal. So this is because if you have a smaller prediction horizon, it will be optimal within a smaller prediction horizon. So you could actually avoid this by increasing the time horizon to almost infinity. So that it becomes optimal, it becomes globally optimal. But now this introduces a trade-off between optimality and the computation. So we cannot take forever to compute an optimal solution. The controller must run at 10 Hz or 0.1 seconds. So we need to implement and control input at 0.1 seconds. So here we have a trade-off between the computation and optimality. So if we are not able to find an optimal solution at 0.1 seconds, we cut off our calculation process and we implement the closest suboptimal solution. Or else the controller will start losing control and it will start wandering around. So what does this mean? So we saw feasibility and suboptimality. So an infeasible solution is that it's not able to stay within the closed set. So in other words, infeasibility directly implies suboptimality because you're not able to calculate the optimal solution that keeps within the set that you have actually designed. But suboptimality does not always lead to infeasibility. You could still have a suboptimal solution and yet stay within the feasible set. So the suboptimality here is because of the cutoff time. Since we wanted an optimal solution, say within like 0.1 seconds or like 0.01 seconds or at 100 Hz. So we had to cut off the computation time and we had to implement a suboptimal solution. But that still keeps you within this set XS that you define. So suboptimality does not always imply infeasibility, but infeasibility always results in suboptimality. And finally, MPC in action. So we implemented this MPC, which is a standard S-curve, which we use for an autonomous testing in AutoDrive, where if you are able to drive it in a sharp S-turn like this, so it will most likely be able to drive in urban roads. So here you see the green point, which is the target position. Like you saw in the first slide, you don't have a set target position at MPC. You keep updating the target position. And the red point you see in the first slide is the current position of the car. So this is an actual car, if you could see in meters, like we tested in the Buckeye lot and CarMax. So it's the actual car that's trying to reach the target position. So the target position keeps updating. So the second point plot you see here is the y-axis tracking and the x-axis tracking. So you see the MPC updating and the reference updating at a time step little ahead of the MPC. So you see so you have the reference being updated at a time step ahead of the MPC. And what you see here is the X tracking results, the Y tracking results, the yaw tracking result, and the total cost function, which reduces, which proves the MPC is stable cost. So we successfully implemented an MPC so far. So we are yet to deal with the problem of having a safe controller. So how do we work on a safe controller? So initial starting point is very simple. We just came up with a safe constraint and added as one additional constraint to the MPC. So we had like 5 constraints in MPC, come up with a safe constraint and make it as 6 constraint in MPC. So for example, the vehicle has a safety radius, the obstacle has a safety radius, and the safety is imposed through constraint. So you can actually calculate the distance between the obstacle, add a safe distance, and then maybe add it as a constraint in the MPC. So that's what we initially did. So we defined a distance constraint, which is the distance between the vehicle and the obstacle. And then we add a DSafe, which is a safety distance. And we always make sure if the safe distance is always greater than 0. And we added this as one of the constraints in MPC. So did it work? Yes, in some cases, we had a static obstacle. And what were the drawbacks that made it not work so good? So the safe distance constraint is implemented in the discrete time formulation, which means it's limited by the discretization of the time. The constraints are rigid. It leads to infeasible solution. It cannot maintain a safe distance. You end up with an infeasible solution. The prediction horizon is short. The controller may not be able to avoid the obstacle. And it also implies that it cannot adapt to a higher vehicle speed due to the discretization of the time and of the control horizon. Or if the vehicle has a higher velocity or an acceleration. So moving on to the CBS implementation. So consider a nonlinear function x dot equal to f of x. So we define a function h which maps from Rn to R over a closed safe set S. So the function h of x within this safe set S is always greater than 0. So in the interior of x, it is strictly greater than 0. So on S, which includes the surface of the safe set, h of x is greater than or equal to 0, and inside the safe set, h of x is strictly greater than 0. So now as you approach the boundary of the safe set, which is denoted by dou s, h of x could be 0. And before we go on, as we move to the boundary of the safe set, we make sure that the h of x increases. So as the x approaches the boundary of the safe set, we make sure that the h of x strictly increases. So by this, we could have an deviation from approaching the unsafe region and make the vehicle move towards the safe region. So as you reach the boundary of the safe set, you modify the control such a way that h of x increases and you go away from the unsafe region. So if you go into the unsafe region, which then h of x becomes less than 0, and then you go away from the safe condition and you go away from the safe set, which does not imply safety. So now we have this function h of x and h dot of x, which actually makes us go away from the unsafe region. And now this could be implemented in discrete time domain and continuous time domain. So in discrete time, which we initially started, which was much easier to implement. So for an n-step discrete time MPC, we implemented the h of x function as follows. So for n time steps, you have the h of x function at time t plus k plus 1. And you have 1 minus gamma times the h of x at time t plus k. So when you have a control input, you implement the control input and you predict where the state would go at time t plus k plus 1. And then you calculate the control barrier function at the time step t plus 1. And then that's your control barrier function. And we make sure it's greater than 1 minus gamma of the control barrier function at the current position. So to make it simpler, so we again have the distance constraint over here. So where we say the distance between the x, the current position at t plus k plus 1 and the obstacle position. And then you have the y position at t plus k plus 1 and the obstacle position. And then you have a safe distance. Similarly, for h of x at time t plus k, you have the current position of the obstacle and the d safe. So here you have the current position, and then you have the position at the next time step that you go upon implementing the control. So you calculate the control barrier function at 2 time steps, the current time step and the next time step over the n intervals of the prediction horizon. So here the gamma that I initially said is a positive coefficient and it's a design parameter. So here the gamma can be tuned which actually gives you a trade-off between feasibility and safety. You see how the gamma has been implemented, it's 1 minus gamma. So if you have a very small value of gamma, so it means it prioritizes safety and you might end up in an infeasible solution. So if you have a very high value of gamma, say 1 and 1 minus 1 becomes 0, so you prioritize feasible inputs and then you compromise on safety by prioritizing on feasible inputs. So now how do we integrate it with MPC? So we have an n step control barrier function at time step 1 ahead and at the current time step, and then we add it as constraint. And then we add it as constraint in the discrete time MPC formulation. So moving on to the continuous time case. So here you consider a nonlinear affine control system, which means that the u is linearly dependent to the function g of x. And then we need to very briefly introduce what lead derivatives are. So lead derivative evaluates the change in a tensor quantity as it moves along the flow of some other vector field. So for example, here the lead derivative on a general manifold M. So this is the entire manifold. Then you have the lead derivative, which is the difference measured by this variable. So it is taken with respect to the smooth vector field eta on the manifold M. And here the lead derivative measures the quantity of eta, how actually changes as compared to the quantity dragged by the vector field. So with the lead derivative in place, we come up with a safe controller where you come up with a control input such that the lead derivative of h of x with respect to the state function, the lead derivative of h of x with respect to the input function is greater than alpha of h. Here, h of x is a control barrier function, and any control that satisfies this condition will render the set as safe. So with h of x with a general f of x, h of x, which is again the distance between the current position and an obstacle, we calculate the h of x. We take the partial derivative of h of x with respect to x with respect to y, and then we calculate the lead derivatives. So which is LF h of x and LG h of x are the matrix, the vector field h of x, the derivative, partial derivative of h of x with respect to x, the partial derivative of h of x with respect to y, along the functions f and g. So how do we implement this in the controller we have? So we implement it through a quadratic program formulation. So we have the MPC that operates, that gives us the optimal control input at every time step. And then we pass this MPC control input to a QP, where the QP is implemented such that it changes the input in a most optimal way, such that it makes the set safe and it's within the safe set. So any input you get from the MPC, you could actually replace this MPC controller by a PID controller or any controller. So it just needs a control law. And then you have a quadratic program formulation, which modifies the control input in a safe way such that you remain within the safe set. So here, alpha that you see is again a design parameter, and it's a strictly increasing class K function. You could have it as a constant, but in general, it's defined as a strictly increasing class K function. So to recap what we have seen so far, we started with the very cool autonomous car we have from Autodrive. We have the onboard sensors, onboard computer that's a perfectly set up. We have the control loop, which has a vehicle dynamics, the vehicle sensor stack, a lateral and longitudinal controller. Then finally, we implemented MPC as a baseline model, and then we had 3 controller formulation which could lead us to safety. So one is nonlinear MPC with discrete time safe constraints. We have nonlinear MPC with discrete time CBF constraints, and then you have an MPC with QP formulation, which is a continuous time continuous time safe controller. So the key takeaway from CBF is any control action U that could keep CBF h of x greater than 0 and render the safe set forward invariant, then the control input U is a safe input. So with that, I'll be passing on the presentation to you with whom I have worked this entire topic with, and she'll be showing you testing and verification.
Next part, we will discuss how we implement these numbers on the vehicle and what kind of scenario we try to verify. So the previous visual said that we implement this on the AutoDrive vehicle and we test the scenario in the compiler. And we also use Python controller Python to cooperate with other like perception or sensor teams. And also we have some predefined information like previous theory. We have the predefined reference trajectory. And we also have the obstacle information. We assume that is already from the perception pipeline. Also, the real-time input is GPS and IMU and the velocity from the canvas. So here we have a safe analysis. We define 3 parameters. The first one is the minimum distance between the current vehicle position to the obstacle position. And the other one is the safe criteria, which is the vehicle radius, cost, obstacle radius, and the safety distance. So if the minimum distance is larger than the safety criteria, we will identify this as a safe condition. So the other criteria is the collision criteria, is that if the vehicle radius cross the obstacle radius, if our minimum distance is smaller than that, it means we must have collision. But if in the mid of these 2 criteria, we will regard it as an unsafe condition. So we use Kazadi as our optimization tool because this is support like MATLAB, Python, and C++. Also, it's an open source software. So we have some important feature we are using. The first one is we can output like all the optimization process. We know the iteration, we know many times for this optimization. And the other one is we can set up the computation cutoff. For example, like we can cut off within 0.1 meters, or we can cut off in 100 iteration. And the other important is the invisibility debugging, because sometimes you may set up some constraint that violate the other constraint, but you might not know. So there is a tool that you can output all the invisibility, so you can check which constraint you are violating. But did it work? So this is how we are testing. As you will try to, we try to avoid the obstacle late. So, and then for this vehicle, it just go somewhere around and then go back. So vehicle just move around everywhere. So why it happens? We try a lot of tests and we found that the computation time is a big issue. So it will impact on the controllability. If you have a really low control input update rate, for example, if you use 1 Hz, which means you just update your control input 1 meters after, then even that your vehicle is traveling with a low speed, just 5 meters per second, the vehicle will move to the next 5 meters and it's like a late control. So for this, we try to optimize our code, like you cannot initial your optimizer in your loop because it's really time consuming. Like once we move the optimizer out of the loop, we can reduce like 90% of computation time. And now even though we include a set constraint, our computation time is almost around 0.03 to 0.03. So we implement this on the different scenario. The first one is the static obstacle one. So in this one is the most common scenario. So we assume that we know the obstacle here, and then we avoid the obstacle. So here we have the h of x with 3 different controllers. So this is the trajectory. So you can see like the total computation time here for different controllers. The QP is the most important, and the CDF and QP is for a safe analysis, which identified as a safe. But for the DC one, it will come into the unsafe area. So we also try another simulation. This is simulation. Like we put like different multiple obstacles on the road, and we have unsafe situation for the control, like this wind control variable. So you can see the actual X violate the all violate a little bit under than zero, so it will become a unsafe situation. And next one is the extreme case, like Vishnu discussed earlier. So we assume that there is a pedestrian just jump into the vehicle, and we want to see if the car hit the pedestrian or not. But Vishnu is still here, so obviously it's not Vishnu. So then we want to analyze more about the trajectory. So you can see the zooming plot here. In the distance constraint, obviously like stay in the unsafe area. But for the CBF, it's very CBF, it cannot predict because it's like a sudden pedestrian dropping. So it cannot predict the position. So it still sit in the unsafe area. However, the QP1 is still keep the safe distance. And the final scenario is that we want to check the ADAS feature, or it's more like a overtaking scenario. So in this scenario, we're trying to in this scenario, like we can see obvious like the QP formulation is trying to avoid the obstacle much earlier than other two controllers. So it's more like it must be a safe situation in this QP formulation. Also, you can see the NPC controller cost is like variable because the obstacle avoidance. Now we want to discuss the extreme case. So this case is like 3 pedestrians sit in a 20 meters by 20 meters area, and the autonomous vehicle will detect one of them within the 5 meters ahead. So in this situation, you can see it avoid the first one, but then this discrete time control barrier function hit the second. So in this situation, it will be identified as a collision situation. But for this one, so the QP1 will avoid this as well. So this QP still be identified as a safe controller. And why it happened? So in previous theoretical part, we already know like the QP formulation is based on the continuous time derivative. So it's more like it provides a field. So it's like a more conservative controller based on the dynamics. But the discrete time is only based on the prediction step, which will make the maneuvers more aggressive than the QP formulation. So in our next step, we are exploring the safety guarantee under measurement uncertainty. So we try to simulate, we put the noise, position noise into the controller. So this is 0.1 function noise, and this is 0.3. Even for the QP, it should be the most safe one, but it still shows like unsafe situation in all the systems. So summary. So back to the first question. So will all the effort can we guarantee the 100% safety? The answer is no. So you can see the extreme case, we might have collision situation. And all these efforts are provided as a mathematical framework. And we also have some practical consideration. So it's like we have perfect perception, we have perfect sensor pattern, and we find the optimal or at least feasible solution based on the computation. Also, we have uncertainty in measurement in the practical. So thank you. Any questions?
There needs to be a disclaimer, no graduate students were injured in the context of the conduct.
I think she made a statement, since they both are here, so that's an
It's
evidence.
proof. And he was so confident in the algorithms that he would stand in the way.
So, any questions, comments? I will warm up the discussion.
I might have a question.
Oh, okay, let's start.
When you're discussing about the safety constraints bound,
Mhm.
how do you came up with the minimum and maximum value?
So for velocity, we just like depends on the velocity range. So if yeah, like all our tests, we did not go at a much higher speed. So all we considered was around 10 to 20 meters per second. And so within this range, we had plus or minus 5 as the velocity. Like for now, we had it fixed, but in our future updates, we plan to make it more velocity or as a function of the velocity.
And coming to the second one, steering, though, how do you evaluated the steering one?
So it's obvious because from the auto drive regulations, we got a steering bound constraint that we need to follow. So that's pretty obvious because we don't want a steering situation that would like provide an extreme left to right in a sudden maneuver. So the rate bound constraint is provided such that we respect
That
the safety or the stability of the passengers in the vehicle. So we just followed that constraint directly. So
Some information is under NDA, right?
Yeah.
So that's good. Good question. I have one question on when we talk about invisibilities and optimality. Go to that slide. Yes. So how do you define your optimality?
So if we are able to calculate the MPC based on the cost function and the constraint, if we are able to calculate a minimum and control input with the minimum cost, that will keep us within the defined state. So this is the MPC formulation. Here you just have the set of feasible states. So if it's going to be the CBA formulation, it's going to be the set of safe states. So
Red states are the safe states. So
red state is the set of states.
set of safe states.
That just the set of states. So
Yeah.
if we go back even further, when we defined the controlled invariant set, we had two sets. We had the red, which is the set of all states, and then we had green, which is the set of safe states. So in MPC, we just consider the states to like define optimality or feasibility at a high level,
At all possible
all
states.
possible states. So if we are able to come up with the minimum calculation, the minimum control effort that will keep within the set that you define. So that's an optimal control. So if you are not able to calculate, so this depends on the control per cutoff as well. So within 0.1 seconds, if you are not able to calculate the optimal input implement, so you cut off the calculation and you implement the closest solution.
Previous solution?
Yeah, the closest solution that you are able to calculate within 0.1 seconds.
Okay.
So that is the suboptimal solution. So suboptimal solution need not always guarantee, like need not always lead to infeasibility. So you could still stay within the defined set and have a suboptimal solution. But if you have an infeasible solution, It means even if you have a very high calculation time, you'll not be able to calculate that minimum input because you don't have a possible solution.
How much you were cutting into 0.1 seconds and to get feasible but suboptimal solution?
So it depends on the controller formulation as well. In the QP formulation, which is the lightest formulation, we were able to come on an average to 0.03 seconds. And in the CBF formulation, we were able to come around 0.05 to 0.07.
So you will lead to more suboptimal solutions in case of FTC formulation.
Yes, in this green time formulation. And since it's also based on the control horizon, so it leads to comparatively higher infeasibility, comparatively higher suboptimality.
What's your control horizon? What's your control horizon?
So
We use 8 steps.
Eight steps.
then the prediction ahead is like 5 meters in front of the wheel.
Did you play with this horizon?
Yes, we did.
Cut in this 0.1 seconds?
Yes, we did. So it was like completely up and down. So and also dependent upon the cap computation of the Intel machine we use for calculation. Like we cannot increase it more than certain value, like we cannot keep it 40 because of the calculation.
Did you try 3 seconds, 5
Yes.
5 steps?
Yes, we did.
So but does that help in this
It helps in some cases, yes. And in some cases where if we increase the velocity of the vehicle, it becomes of no use.
So then what's the velocity constraint on it? So within what velocity range you can operate this?
So right now we are having and we are planning of a multi-color simulation where we try a range of velocities, a range of constraints, a range of cutoff times, a range of prediction horizon to actually see how good it would perform and in what cases it performs well and in what cases it does not. So we are currently working on it. But right now we randomly saw some status like the extreme cases and saw that if it worked or not.
What is your speed as of in the experiment? What was the speed?
So in an actual simulation, it was 78 meters per second while testing on the vehicle. And in simulations, we went up to 15 to 20 meters.
The simulation speed was more, right? But you cannot run with the same speed on the actual vehicle
Yeah, in the party.
because you need more computation power. Or this was this part.
We weren't able to test it actually.
So if you were to test at TRC, you can do this.
Yeah.
Speed. So it's not the onboard computing limit.
We don't have chance to test.
You were not able to challenge the onboard computing. Any questions online or? There are no questions. Thank you, representative.